Okay, welcome everybody. So this talk is entitled Lambda, a Peek Under the Hood. There are a lot of talks about Lambda here at DevVox this year. You just saw a little bit about it at the keynote, and there was a hands-on lab yesterday, there was a tutorial yesterday, and there's quite a few sessions spread throughout the conference. So what I'm going to talk about today is, in some sense, a completely useless aspect of Lambda, in the sense that it's not going to help anybody in their job immediately, right? You know, I could get up here and give a talk about what Lambdas are and how to use them and all of that, and I assume most of you have probably seen some of the introductory material. So what I'm going to talk about today is how is it actually implemented? What's the VM doing? So, of course, I'm obligated to put this slide up. I work for Oracle. This is how you know I work for Oracle. I'm not an imposter. So I'm going to talk about the technical details of how Lambda expressions are implemented in Java SE8 at the bytecode level, and what the various players are in this system. You have the compiler, you have the language runtime, you have the VM, and how they sort of work together. Now, there's going to be a lot of nuts and bolts here. I'm assuming people are familiar with not just the Java language, but the JVM and JVM bytecode. Let's do a little sanity check here. How many people here have used the Java P tool to dump out bytecode? All right. So anybody whose hand isn't up is probably going to be lost, but that's okay. So I'm going to talk a lot about, I'm going to show a lot of bytecode on the screen. I'm going to talk a lot about how this interacts with the Invoke Dynamic facility that was added in Java 7. And at the end, I'll give some performance numbers about where we are performance-wise right now. Okay, so I'll do just a quick recap of what Lambdas look like in the language, just so everybody's on the same page with the syntax. A Lambda expression is an anonymous method. It has everything a method has. It has an argument list. It has a return type. It has a body. Its arguments have types. There's a set of thrown exceptions. It's a more syntactically compact way of describing a method. So in the first example here, we have the argument of the for each method is a Lambda expression. Its argument list contains one item whose type is person, and its body evaluates the expression names.add of e.getName, which is going to be void, and so it's nominally this Lambda expression is a function from person to void. Now, the compiler does a lot of work to make our lives simpler. So, for example, the second line of code here means exactly the same thing. You're asking the compiler to infer the type of the argument e, which is not doing, it's not dynamic typing. There's nothing new and scary going on here. It's exactly the same code, but it's looking at the signature for each and saying, I'm expecting some kind of function from a person to void, and so e must be of type person. And then it type checks the body and says, oh, yep, the body type checks. If e is person, everything's good. Now, the body of a Lambda expression is allowed to refer to values that are declared not within the Lambda, but from outside in the enclosing context. So in the last example here, we're saying take the collection of people and remove all the ones that match the criteria where their age is less than some minimum age. And minimum age is a variable from the local context. Maybe it's a field, maybe it's a local variable. Doesn't really matter. But the point is, Lambdas can refer to things from outside their scope. Okay, so that's basically enough Lambda syntax to be able to motivate the examples that I'm going to use here. Sort of backing up to the big picture a little bit about why are we doing this. There's a lot of reasons to do Lambda expressions in Java. One of the most important is that this is a path to a programming model that is relevant in today's multi-core age. We want people to be able to write code that is not intrinsically sequential or intrinsically parallel, but works in both. The best way to do that is by delivering parallel libraries. In order to deliver parallel libraries, you need a mechanism called internal iteration. That's basically saying, here, for each element of the collection, do this thing. And in order to have that, you need a concise mechanism for passing behavior as data so that you can pass in the thing to be done for every element. Now, of course, that's not the only benefit. There's lots of cool things library writers can and will do once Lambda expressions are in the language that allow you to write code that's easier to read, easier to maintain, more obvious what it does. And of course, we're mindful of the fact that we may have fallen a little bit behind the competition, and a lot of other languages already have Lambda expressions. So a lot of the things that Lambdas let you do, we've been able to do sort of for a long time with interclasses, but it's so clunky that people don't want to do it. And this clunkiness is not just syntactic. The clunkiness is also semantic. If you look at the semantics of interclasses, name lookup in the context of interclass, when you see a variable x inside an interclass instance, what does it mean? Well, it could be inherited from the enclosing context, or it could be inherited from one of the supertypes, and there's complicated rules for managing this. Lambdas are a lot simpler in that way. But what I'm going to talk about in this talk is runtime representation. When you type code like on the previous slide, what bytecode does the compiler emit? What does the VM do with it? And why did we make the choices that we made? And the reality is that runtime representation matters. It might be tempting to say, well, just design a language that's sensible to use, and let the implementation figure it out, how to run it efficiently on the JVM. But the reality is, if there's a mismatch between how things look at the language level and how they are represented at the VM level, this is going to be a lifetime subscription of pain. The sharp corners always show through when you do that. So we wanted to have a story not only for what should the language look like, but how is it represented sensibly in the VM so that the two are not at odds with each other. Okay, so the biggest question, if you add a new kind of expression to the language, the first question in a statically typed language like Java is, what's its type? What is the type of a Lambda expression? If you look at other statically typed languages that have Lambda expressions, say Haskell, the type of a Lambda is a function type. A lot of languages that have Lambda expressions have a notion of function type in their type system. Function from int to int, function from Boolean to void, etc. So we could have done that. In fact, most of the early proposals for adding Lambdas to Java said, and the way to get there is we're going to add function types. And this is an obvious idea. This is how other languages do it. A Lambda expression is a function, so its type should be a function type. But then when you start digging into what does that really mean in the world of the JVM, what does the bytecode look like, you start getting to some very nasty questions. So, for example, what would the bytecode signature of a Lambda be if you have, say, a method that returns a function or a method that accepts a function? When you invoke a Lambda, what bytecode would you use to invoke it? How would we create instances of them? In the Java bytecode, we have the new bytecode for creating new objects, and we have new array for creating new arrays. How would we do this for Lambdas? And how would we deal with language-level concepts of variance, where this might be a function from question extends foo to something else? How would we represent that in the bytecode? These are all pretty difficult questions. And what we didn't want to do is to say, well, in order to have Lambdas in the language, we need to add like 12 new bytecodes to the bytecode instruction set. That might have been fun, might have been an exciting engineering project, might have been useful to other languages besides Java, but it would have distracted us from getting to where we wanted to go in a reasonable time. So the problem is that there is no way to natively represent a function type in type signatures for methods or fields in the class file. The closest thing we have is generics. We could say, a function from int to int is really an instance of some interface, capital F function with two generic type parameters, integer, comma, integer. But that means that our function types, if we had gone that way, would have been boxed, ugh, and erased, double ugh. So, and this would have created this gap between what you're saying at the language level and what you're saying at the VM level, and that's always painful. So teaching the VM about real function types would have been this huge effort, new kinds of type signatures, new bytecodes, new rules for the verifier, etc. So we started casting around looking for some alternative ways to do this. So we looked at how things are modeled in real-world libraries. And most real-world libraries model function-like things using single-method interfaces, runnable, callable, action listener, etc. So rather than do this incredibly complicated thing to the type system and this other incredibly complicated thing to the VM, why not just formalize this notion that we've been using for years? And one of the ways you formalize something is you give it an official name. So these methods, these interfaces like runnable and comparator that have one method that in the past were just interfaces, now they're a special kind of interface. They're called functional interfaces. And the compiler recognizes them as functional interfaces by looking at their structure and saying, okay, this is something that has one method. I'm likely to use this to represent a function. And the compiler will do conversions between instances of a one method interface like predicate and a Lambda expression like you see in the bottom example. So what the compiler does is it sees the signature of removeIf, and removeIf takes a predicate. And it says, okay, predicate's one of these special interfaces. It has one method. Its signature is t to Boolean. So it's a function from t to Boolean. Let me see if I can make this Lambda expression work under that type constraint. Well, there's one argument, so we'll infer that as being a t, and we'll type check the body of it and say, oh, yep, that evaluates to Boolean, and we're good. So the compiler decides, yes, this Lambda expression is compatible with the type predicate of t, and it converts it to a predicate of t. This all happens structurally. There's nothing predicate has to say in order to be eligible for this treatment. And then type inference says that, in fact, the Lambda expression converts to predicate of person and infers P as being person. Okay, so this is actually a lot simpler than the, quote, obvious way to do it, and is more in line with how we've been writing libraries in Java from day one. So the lesson here, and this is, you'll see this theme repeat, there was like an obvious and wrong choice. So it was really easy to say, well, just add function types. And everyone said, oh, yes, that's obvious. We'll just add function types. And then you find out what just adding function types entails, and the complexity just balloons out of control. It also, if we had done this, we would have divided the world of Java libraries into old libraries of pre-Lambda and new libraries post-Lambda, and there would have been compatibility issues, and there would have been all of this effort of, let's rewrite all these libraries to use the new stuff, which is a big waste of effort. So instead, by adopting a pattern of coding that people have been using in Java libraries for years, those old libraries are now forward compatible to Lambda, even though they were written at a time that didn't imagine Java would ever have Lambdas, which is a pretty cool trick. So not only did this make our lives easier in implementing Lambda, but it also maintains our significant investment in the libraries in the Java ecosystem. So it's kind of a lesson here. Sometimes, the stodgy old way of doing things is actually better than the shiny new one. All right, so let's move on. Next question that's obvious to ask is, what is the representation of a Lambda expression? How do we create an instance of a Lambda expression? What bytecode do we generate, etc.? So if we have code like this, we say have a predicate of person, and the right-hand side is a Lambda expression that takes a person and asks whether their age is less than some minimum age. We need to generate code such that that results in an instance of the interface predicate. And we have to deal with things like, I've captured this variable min age from the enclosing context. So again, there's an obvious choice here. And that is, let Lambda expressions be syntactic sugar for interclasses. This was one of the proposals that was made before the start of this iteration of adding Lambdas to Java. So that would have been really easy, and we could have gone home relatively quickly if we had done that, where we would say a Lambda is just an instance of an inner class, and when you saw the Lambda expression that I'd showed on the previous slide, the compiler would generate code like this, generate an anonymous class, foo$1, it implements predicate, it has a field to hold the captured variable, it has a constructor that accepts the captured variable, and it's one method, all it does is execute the body of the Lambda expression. That would have been really simple. And similarly, invoking the Lambda expression would also be really simple. When the compiler sees this, it would say, okay, well, really, I need to generate this synthetic foo$1 class, and then at the point where I need one of the Lambda expressions, I just invoke its constructor. This is what the compiler does with inner classes today. And that would have been really easy. If you look at this at the bytecode level, bytecode is also pretty straightforward. If we were generating it, as I showed on the previous slide, so the invocation of the remove if method is first get the list, push it on the stack, create a foo$1 object, push the captured variable age on the stack, and invoke the constructor. And now on the stack we have the list and the predicate that we want to pass to the list, and then we just invoke the interface method remove if. So that would have been easy. Like I said, we could have been done in an afternoon. So why didn't we do that? Well, as I mentioned earlier, interclasses have some problems, and translating to interclasses means that we would inherit most of the problems of interclasses. One of those problems is performance issues. You get one class per Lambda expression. Another is because you have all of these classes, at the VM level you end up with type profile pollution, where you have a method that accepts a runnable, but the VM isn't able to do any kind of prediction on exactly which type of runnable am I going to see here that it could use to do inlining or inline caching or any number of other tricks the VM uses to get better performance. And also, if we're representing a Lambda as an interclass, we're always allocating a new instance even when you don't need one. Semantically, it would have also been complicated to do it this way. If Lambda expressions were just syntactic sugar for interclasses, we would have inherited the complicated name lookup mechanism that interclasses have. Now, the thing to recognize is whatever we did in version 1 would effectively become a binary representation for what a Lambda looks like in Java class files, and we will be stuck with it forever. Ideally, we don't want to have a binary representation that tells you exactly how to do it. We want to have a binary representation that tells you what to do. By avoiding conflating implementation with binary representation, we have more flexibility to implement things in a more performant way in the future. So the just use interclasses choice was another one of those things that was obvious and wrong. Okay, so if we're not going to do that, what else are we going to do? Well, if you go back to the features that were added in Java 7, there were a number of JVM features added in Java 7. One of them was called method handles. Now, this is an API for dealing with VM-level function pointers, basically. And there are combinators for composing method handles and moving their arguments around, et cetera. And this is mostly a tool for compiler writers. Ordinary application developers don't write code that use method handles, but compiler writers love it because you can generate method handle constants into the constant pool, and the VM will treat that as a constant load, and you can get a method handle for any method and combine them and do things with it. You can adapt one method handle to another using adaptations like casting and boxing and unboxing, etc. So great tool for compiler writers. So another obvious question, why not just use method handles? And at first, this seems like a really great idea, because a Lambda is a method object at the language level, and a method handle is a method object at the VM level. So it's a match made in heaven, right? So all we would have to do in this scenario is, for each Lambda expression, desugar it to a method. So take the body of the method out of the Lambda and stick it in some method called, Lambda $12. And then we would represent in the bytecode signatures lambdas as method handles. So let's take a look at what that looks like with our same example. So the first step is we have the body of the method, p.age less than min_age. We need to desugar that to a method. Well, that's really easy. The compiler can do that. It makes up this lambda $1 method, which actually takes 2 arguments, not 1. Because we have to have room for min_age. So whatever the shape of the function described by the functional interface predicate is sort of the second half of the argument list. And then whatever variables are captured by this particular Lambda is the first part of the argument list. So here we have one captured argument and then one argument in our functional interface. And the bytecode that would be generated for this call to remove if would be something like load a method handle constant out of the constant pool that corresponds to the static method lambda $1, and then use the method handle combinator insert arguments to stick the min_age captured argument into that, and now that's a method handle, and pass that to remove if. So the signature of remove if would be remove if method handle. And this is where this idea kind of falls apart, because method handles aren't typed. They're even more erased than generics. You don't even know what their arity is. That the compiler's supposed to know that and generate the appropriate method handle code. They're dynamically typed, so if you pass the wrong number or wrong type of arguments, you'll get an exception from the runtime library. But if we did this, now you wouldn't be able to overload two methods in the same class where one takes a function from, int to Boolean and another takes a function from person to string. And that would be even more confusing than the current restrictions of erasure. And still, we would have to encode the type information that was erased somewhere and put that in the class file. So, seemed like a really good idea. But when you sort of dig through the details, it turns out to offer a bad experience to the user. And again, this approach has the exact same problem as the previous approach, which is we're conflating our binary representation. A lambda is a method handle. That's what what shows up in the bytecode signatures with the implementation details. So another obvious but wrong choice. And you wonder why this took so long. We had to work our way through all of these obvious but wrong choices and figured out why they're wrong and then back up. So let's step back a moment. So what we'd like is a binary interface that isn't tied, a binary representation of lambdas and class files that isn't tied to a specific representation, specific implementation, sorry. Interclasses, they have too much baggage, method handles were erased, and we don't ever want to put users in a position of saying, oh, we came up with this great new way to compile Lambda expressions. All you have to do is recompile all your Java classes. We're not willing to ask our developers to do that. Some languages are, we're not. So the way that all problems in computer science are solved is with more layers of indirection. And the art to solving problems with additional indirection is making sure that this indirection doesn't cost you anything performance-wise. So the basic idea is we would like it if the compiler would omit a more declarative recipe for this is the kind of lambda I had in mind, rather than imperative code of create a new instance of this inner class and pass this to its constructor. And then the runtime would say, okay, you want a lambda. I happen to have a good way to make lambdas. I'll use that. Tomorrow, they have a better way to make lambdas, and tomorrow I could use that. So as long as we can make this fast enough, this is a win. Now, to do this, we turn to another tool that was added to the VM in Java 7, which is Invoke Dynamic. So Invoke Dynamic was the first new bytecode added to the bytecode instruction set in like forever. And it was originally designed to make life easier for dynamic language compiler writers. And we said, well, why should those guys have all the fun? This is a pretty cool tool. I want to use it in my statically typed language too. So the bytecode instruction set prior to Java 7 had 4 bytecodes for invoking methods. 3 of them corresponded to types of methods in the language, static, virtual, and interface. And then there was this kind of grab bag bucket called invoke special for kind of everything else. So super calls and constructor calls and things like that. But the thing that's common to all of these invocation modes, and we've seen this bytecode we've seen before, is they name what class holds the method that I'm calling, what is the name of the method, and what is its type signature. I kind of alluded to this in the keynote. This is like the most static part of Java, where when you do overload selection at compile time, it picks an exact type signature, like their function from int to void, or function from predicate to Boolean. And it actually sticks that in the bytecode, right? So it statically selects the signature and puts the signature into the bytecode. So Invoke Dynamic is a 5th invocation mode, and the idea is the other invocation modes are they have these fixed semantics that are very much tied to the Java language semantics, and that works for a lot of cases, but it doesn't necessarily work for all languages. And so it's a way of specifying custom method linkage where a language can say, I've got this call site, and at runtime, I'll help you link it. So basically, the idea is when a compiler emits an Invoke Dynamic into the bytecode, it's also supplying what you might call some, quote, language logic to help resolve the call site, at least the first time that that call is made. And we talked about how this is another level of indirection. You don't want to be indirecting through that language logic on every invocation, because that would slow things down a lot. That would kind of be like invoking things reflectively, which is kind of okay if you're doing it once, but if you're doing it a lot, it's not going to be fast enough. So the idea is the language and the VM kind of become partners. The language says, I'm going to contribute some logic in the form of here's some Java code to link the call site, which the first time you invoke this call site, I'm going to help you find the target. And then I'm going to return a target, and I'm going to return some extra information that you can use to decide whether you ever have to ask me again or whether you can cache that result and just let me get out of the way. Okay, so you could imagine, the Groovy compiler emits some code, and it points to some Groovy-specific logic, or the Jython compiler emits some Jython-specific logic, and in the end, these all map to method handle targets that the VM already knows how to inline through and do all kinds of tricks with. Okay, so Invoke Dynamic started out as this tool primarily for dynamic languages. So, for example, in a language like Ruby, you might write a method like this. I've got a method called add. It takes 2 arguments. I have no idea what their types are, and I'm going to add them together, even though I have no idea whether you can add those 2 things together. And the idea is at compile time, we don't know what A and B are. They could be int, they could be float, they could be shoes, who knows. Theoretically, on every invocation of add, I could give you 2 different types. This time I'm going to add some floats. Next time I'm going to add some booleans. Next time I'm going to add some floats. We could do that. But in the real world, it usually doesn't work that way. Usually, if I have a call site, like the call to the plus method inside the body of add, if I just called it with 2 ints, next time I call it, I'm probably calling it again with 2 ints. As a result, if I kind of make that optimistic assumption, and then in the case when I'm wrong, back off and generate some more code, we can win pretty big by saying, all right, sanity check here, 2 ints, yep, okay, just treat them as ints. So the win of Invoke Dynamic is you have some language logic that helps you link the call site and say, what code am I really branching to when I invoke this method? And then language logic gets out of the way by saying, yeah, you don't need to ask me again, or you only need to ask me again if the type of this thing changes, or something like that. So the first time the JVM stumbles across an Invoke Dynamic bytecode, it does this one-time linkage thing. It consults the language logic, which we call the Bootstrap Method. And what the Bootstrap Method does is it looks at the call site. It has all the information about the call site. What's the name? What's the arguments? What's the static type of the arguments, etc. What's the signature of the thing I'm trying to link? And it returns what's called a linked call site, which embeds a method handle, which describes the actual target that I want to execute. And that method handle could be a method handle to an existing method, like string.length, or it could be a method handle to a method that the Bootstrap method just magically invented. It spun some bytecodes, called the class loader, said load this class, and now give me a method handle to the method of the thing that I just spun. And then the call site can also embed the conditions under which the VM should relink the call site, if any, and hopefully you never have to do that, and then the VM just goes to town and inlines through it and all of that. So after linkage happens, which is to say after the first time you execute an Invoke Dynamic call site, the VM treats the site as linked and can inline through it just like anything else. And that's where the magic comes from, right? Once the language logic has gotten out of the way, the VM can do all the optimizations that it would do with any other invocation. Okay. So what does an Invoke Dynamic call site look like? So a typical call site has, like I said, describes a method by class, name, and argument list. And it has some arguments on the stack. Invoke Dynamic has some extra stuff. It has all of that, and it has what we call the Bootstrap method, the language logic, and it has a static argument list, which is static metadata about the call site that the compiler has emitted into the constant pool, and that's available to the Bootstrap as well. So that includes all kinds of type information, like in the case of Lambdas, what functional interface type am I converting this lambda to, like predicate or function or what have you. And for the dynamic argument, the things that are pushed on the stack, the Bootstrap doesn't see those because this is all happening before the call is executed, but it can see what their static types are and how many of them they're going to be. And then it creates a method handle that takes that many arguments of the correct type, and then those arguments are going to be passed to the appropriate method handle. Okay, I know this is pretty abstract. I'll show some examples about it. Hopefully that'll make it clearer. So, question you might ask, this thing has dynamic in the name. It was for dynamic languages. Why is the Java compiler using it? After all the types involved are static. But what's dynamic here is not the typing. What's dynamic here is the code generation strategy. So I already outlined two possible code generation strategies for lambdas. One of them was spin an interclass. And another is use a method handle to describe the lambda. And I could make up some more. We could use dynamic proxies if we were really patient. Or maybe, our VM has some special private API for constructing objects out of raw bits, and maybe we would use that instead. So we have a dynamic strategy for turning a description of a lambda into an object that implements the appropriate interface. Using Invoke Dynamic here allows us to turn this strategy into a pure implementation detail. The binary representation in the class file doesn't change, but the implementation strategy in the VM could be different from one version of the VM to the next, could be different from Monday to Tuesday, could be different across our VM versus IBM's VM, for example. Okay, so this is a pretty powerful trick. So, having absorbed all of this background about Invoke Dynamic, how do we use it? So we use Invoke Dynamic to embed a recipe for how to make the lambda into the into the class file. So there's an Invoke Dynamic call site, and the recipe includes a bunch of things. We've desugared the lambda body into a method. I showed an example of that earlier. So a method handle for that body is going to be one of the static arguments to the Bootstrap. The functional interface type that we're converting the lambda to, like predicate, that'll be one of the static arguments to the Bootstrap. Any other information we want to pass about how to make this lambda, like for example, the code writer has asked that this lambda be serializable. That would be static information we could put in the static argument list for the Bootstrap. And then any values that are captured from the lexical scope, like min-age, we push them on the stack like any other invocation. So we call this capture site the Lambda factory because it's a call site which, when invoked, it returns you the lambda that you want. You invoke it not with invoke virtual or invoke static or invoke interface, but you invoke it with invoke dynamic, and it returns an instance of the functional interface you want, your lambda object. Now, the first time you capture a lambda at a particular point in the code, you're going to pay the price of this linkage. We'll see some numbers there. It actually turns out to be less than you think. And then subsequent captures bypass the slow linkage path, and they just call the fully linked lambda factory directly. Okay, so let's look at some more code. So first step, like before, desugar the lambda to a method. So we make a signature whose arguments are the functional interface arguments prepended with any captured arguments. Simple lambdas can desugar to static methods. Lambdas that capture fields or other class members can desugar to instance methods. So if they need access to the receiver, we'll make them instance methods, and we end up with a method like this. So then, at the point at which we actually need this lambda expression, we generate an invoke dynamic instruction. So we say predicate, $P is going to be an invoke dynamic whose bootstrap is the language logic corresponds to I want to make a lambda. We call that the lambda meta factory because it's what links the lambda factory call site. The static arguments are what class am I converting this lambda to, and what method describes the body of my lambda, and that's just this this method that we've desugared. And there are going to be some dynamic arguments pushed on the stack. In this case, one of them, it's an integer min-age, right? And we use that to create our lambda object. And then we just pass the lambda object to remove if because it's already an interface of predicate, right? So we're going back to this simpler model where the type of a Lambda is a functional interface. The signature of remove if is going to be something that takes a predicate. So the Invoke Dynamic creates a predicate, and we just pass it, and everything's good. Okay, so what should the metafactory do when it goes to link this call site? Well, it has a choice. One thing it could do is say, well, you know, the compiler uses this strategy for making interclasses. I'll do the same thing at runtime. I will spin some bytecodes that describe something like an interclass, kind of like the same class the compiler would have, but doing this at runtime. And then what I'll do is I'll hook up the Lambda factory site to point to the constructor for that interclass. This is actually the strategy that we're going to market with for Java 8. We sort of view this as the simplest thing that could work. It already performs better than interclasses, so we're not taking a performance regression against the old ways to doing things. But we know that there's lots more we could do in the future to make it faster. So for example, one of the defects I mentioned about interclasses is this annoying one class per instance problem. We could have a metafactory that instead spun a wrapper class, one class per functional interface, whose constructor took a method handle and passed that method handle to the constructor. So instead of spinning one class per Lambda, tomorrow we could be spinning one class for runnable, one for comparator, one for action listener, and reduce the number of classes we're generating. Again, completely bytecode compatible. The bytecode doesn't change. The only thing that changes is the runtime implementation strategy. Similarly, we could use some of the other mechanisms I talked about. We could use dynamic proxies. We could use some other mechanism for building objects. Anything we can think of, since we've deferred this decision to runtime and it's a pre-implementation detail, we can just do the fastest thing. And we could choose to do different things on different platforms. So for example, you saw in the demo, the Raspberry Pi, well, they have relatively small amount of memory. So for Java embedded, we might prefer to choose a strategy that generates small footprint lambdas. And on Java SE for desktops and servers, we may prefer a strategy that lets us generate faster lambdas. And that's purely a runtime implementation choice. The user can't tell the difference from the outside. So this is a pretty cool trick that we've discovered. Invoke Dynamic has given us an opportunity to procrastinate. We didn't have to burn the decision of how we represent lambdas into the bytecode. All we had to do is agree on a binary representation, and then we can change our implementation strategy dynamically. So we pick our binary protocol now, we delay the choice of code generation strategy to runtime. This is kind of consistent with an approach of how things have been working in Java for a long time. Move as much of the work to runtime as possible. The dynamic compiler has more information. With more information, it can make better decisions. So we don't want to burn statically into the class file all of this, you must do it exactly this way, if we can leave some room for implementation choice to the compiler. And this lets us change our code generation strategy from version to version, day to day, VM to VM, etc. Another cool trick is that something that falls out for free from this is lazy evaluation. So most of you have probably done the trick of you had code that says, comparator C equals new comparator interclass goop. And then you observed in your code that, gee, this thing doesn't have any state. Why am I making an object every time I use it? Why don't I say private static final comparator C equals, and then that same goop? Who here has done a trick like that in their code? Right? We've all done it, right? Well, it's a good trick, but it's kind of annoying that we have to do it. That trick falls out for free with lambdas. So what happens is the Lambda metafactory looks at the structure of the Lambda and says, are you capturing anything from your context? And most Lambdas don't capture anything from their context. Most Lambdas are things like, person arrow p.getName. So that's a function from person to string, and it doesn't capture anything. In that very common case, the metafactory looks at it and says, well, not only have I linked the call site, but I don't have to make a new instance every time you invoke this call site. I'll just cache an instance at the call site, and when you call it, I'll just return that. And the VM sees that and says, oh, I know what's going on there. That's a constant call site. I don't actually have to invoke the Lambda factory method. I'm going to turn that into a constant load. So the result is that we've automated this trick of like pulling stateless objects into static fields. We still get lazy initialization. We defer the initialization cost to first use rather than doing it statically in the static initializer. Without like putting any extra footprint into the class or anything like that. And then all stateless lambdas, which is like more than half of them, get this lazy initialization and caching absolutely for free. You write the code that you mean to write, and you don't have to think about, oh, do I have to pull this up into some other variable? The compiler figures it out, does the right thing for you. Pretty cool, huh? But wait, there's more. We used Invoke Dynamic for lazy initialization. We used it for caching. We use it for indirection. So we can defer the code generation strategy to runtime, but that doesn't mean we have to pay for code generation every time we invoke a Lambda. So the meta factory is invoked once. In the non-capturing case, subsequent calls to the Lambda factory are free because the VM optimizes this to a constant load. And in the capturing case, we link the call site to the constructor of the class that we just spun, and the subsequent capture cost is on the order of a constructor call, just like with interclasses. And so we have this nice performance behavior of the worst case is exactly the same as interclasses, and the best case is much better. It's what game theorists call a dominating strategy. Okay, so show me some numbers. First, let's categorize the numbers that I'm going to show you. Any scheme for translating lambdas to objects at runtime is going to have cost at a couple different layers. So we can divide them into linkage cost, capture cost, and invocation costs. The idea is linkage cost is the first time you evaluate a certain lambda that shows up in your code, or an interclass that shows up in your code. The capture cost is the cost of subsequent times that you stumble over the same code. And the invocation cost, finally, is the cost of actually calling the Lambda or calling the method on the interclass instance. So in a world where we had only interclasses, the way these would correspond is the first time you instantiate an interclass of a certain type, the VM has to go out to the file system, pull the foo$1.class bytecodes off the disk, go through the class loader, load the class, and then instantiate the, then it can call the constructor and instantiate the object. So that, go out to the file system, get the class file bytes, and pass them to the class loader and turn that into a class, verify it, all that stuff, that's your linkage cost. Interclasses have a pretty high linkage cost because they involve, in the worst case, disk I/O, and they involve class loading. Capture cost with interclasses is pretty simple. Invoke the constructor of the interclass. Constructor invocation. And invocation cost is call the method of that of that interclass, the apply method or the do whatever it is method. Okay, so let's compare those. First, we'll start with linkage costs. So we had our performance team measure some linkage costs. The numbers you see here are time in milliseconds for linking 32,000 distinct either interclasses or lambdas. We have four rows, one describing non-capturing lambdas and one describing capturing lambdas, and then the other axis is whether we're using tiered compilation or not, because that really kind of messes up a lot of performance measurements. We also, because we didn't want to cheat, we got a really fast disk, an SSD disk, so that the anonymous classes didn't get unfairly punished for having to go out to disk to load the classes. So what we see is in the non-capturing case, the happy case, the linkage cost, not the capture cost, just the linkage cost, was on the order of 10 to 15% better than anonymous classes. And in the case of capturing lambdas or capturing interclasses was even more so, on the order of 20 to 25% faster. Okay, so a lot of people who, when we started this effort, they looked at our approach, they said, oh, you're using InvokeDynamic, it's going to be so slow, it's going to be slower than interclasses. Nope, faster than interclasses. Okay, let's move on to the sort of the second category of costs here that we measured. And this is capture cost. Now, this is slightly different units here. This is operations per microsecond. So we ran this on a big honkin' machine, 4 sockets, 10 cores per socket, 2 threads per core, so 80 hyperthread server. And what we measured here is operations per microsecond for just 1 core, allocating either interclasses, non-capturing lambdas, or capturing lambdas. And then the saturated case is spin up as many threads as we have hardware threads and have them all pound on evaluating or instantiating lambdas and interclass instances. So in the first column, the single-threaded column, for an interclass and a capturing lambda, we had kind of exactly the same numbers, which is kind of what you'd expect, because that's the implementation strategy is just generate your interclasses at runtime instead of at compile time. And for non-capturing lambdas, we got a nice little boost over interclasses because interclasses always capture the enclosing this reference, whether they need it or not. And lambdas only capture that if it's actually needed, and that shows up in the in the timing numbers. Where things get really good is when you look at the multi-core case, right? So in the interclass and capturing lambda, where you're actually invoking a constructor of something, you have to actually make an object, allocate space from the heap, and set its fields. We again saw roughly the same throughput, about 5x over what the single-threaded case was. So not great, but not terrible scalability. But in the happy case, where we automatically cached the lambda at the call site for stateless lambdas, what we saw was, something almost like full hardware speed up. We saw a 67x speed up of how many lambdas we could make using 80 threads over using 1 thread. Okay, so and what that points to is we've taken the allocation out of the bottleneck path. You're basically down to the speed of constant load. If this is operations per microsecond, so that's 1/15 of a nanosecond on average. That's that's pretty good throughput. And I'd point out that this is just using the stupid strategy. Okay, we picked the stupid strategy because we knew we could make it work and ship it, and it's already faster than the old way. We've got a pretty deep pipeline of better strategies. We know this is the stupid strategy, and yet it's still either as fast as or faster than interclasses across the board. Invocation costs, exactly identical. You create an interclass that was generated statically, you create an interclass that was generated dynamically, you invoke its methods, exact same code path through the VM, exact same performance. Okay, so another cool thing about this approach that we've done is we designed this mechanism, this language logic for Lambda conversion, for the needs of Java, but it actually may work very well for other compilers as well. So all of the code for this is public. It's in the JDK. It's in the Java Lang Invoke package. So compilers for, say, Groovy might decide to use this mechanism as well to represent closure-like entities. And if we continue to improve the performance going forward, those other languages will automatically get the benefit of performance improvements in this API. So we expect that other languages are going to want to use this anyway, because even if Groovy closures look different from Java closures, you're likely in your Groovy code to be calling Java class libraries, like collection methods, and you're going to want a way of instantiating instances of these functional interfaces. They might as well use the same code path the Java compiler does, because then they get all the benefit of our optimization. So a little bit of crystal ball gazing here. How might future VM support make this even better? One of my favorite tricks that we have on the drawing board is the VM could recognize these Lambda capture sites. It could say, oh, there's an Invoke Dynamic whose bootstrap is the Lambda Meta Factory, and it just so happens by total accident that the semantics of a Lambda capture site generated by the Java compiler match exactly to certain method handle algebra semantics. Total accident. As a result, the VM could look at that and say, oh, I know exactly what that does. I'm going to replace it with this jumble of method handles. And then I can do all kinds of other optimizations on Lambda, like code motion and box-on-box elimination and all of that, and further reduce the capture cost of Lambda. So there's a pretty deep pipeline of things that we can do to make these costs even lower and move more code from the category of looks like a capturing Lambda to looks like a non-capturing Lambda. The way to think about this is you can think of Lambda capture essentially as a boxing operation. The functional interface, predicate function, what have you, is like a box for a function pointer. Invoking it is like the unbox. So most of the techniques for box and unbox elimination are already present. You need code motion to move the box code to closer to the unbox code. In order to do that, we need to be able to intrinsify the capture site. And then if you're passing a Lambda into some method, if you inline through it, you move the box and unbox closer to each other, you do some escape analysis on the box, you say it's non-escaping, you can eliminate the boxing entirely. Right? So this is a relatively small piece on top of optimizations that the VM already does that would unleash some really powerful additional optimizations on top of the fact that, as I've said, it's already faster than interclasses. I have to keep saying that. Okay, so no language feature is complete without paying some homage at the altar of serialization. Actually took a tremendous amount of time to deal with the serialization aspects of Lambdas. Lambdas aren't serializable by default because we're not stupid, but if you want them to be serializable, if their target type is serializable, like you have a functional interface that extends predicate and serializable, the compiler will say, okay, I have to make a serializable Lambda, I'll do some extra horrible stuff, hold my nose, and you'll get a serializable Lambda. The reason for that is, if you had code like this, and that functional interface has one method, okay, fine. Users will expect this code to work. People want to ship functions across the network because, let's say you're doing some a distributed Hadoop query, and you want to be able to ship your mappers and reducers across the network. So we need to support serialization. Unfortunately, we can't just serialize the Lambda object. Why? Because we generated it at runtime. Serialized form of an object has the class name in it. That class name doesn't exist statically on the disk. So when it gets to the other side, it's going to say, what class is this? I've never seen this class before. So, and even if it did, the other VM that you're deserializing on might be using a different Lambda implementation strategy than the one we're using. So if we have a dynamic translation strategy, we need a dynamic serialization strategy to match that. And of course, we have to do it without exposing the gazillion security holes of serialization. So just as we did the trick of the binary representation of Lambda in a class file as a recipe for the Lambda, that's what the serialized form has to be also. The serialized form has to be, I found a Lambda, its target type is X, the method that it describes is Y, its captured arguments are these serialized things, and fortunately, serialization gives us an easy mechanism for that, which is read, resolve, and write, replace. So instead of just serializing the Lambda object, what we do instead is we serialize the recipe, we ship that across the wire, and we actually have an alternate meta factory for that, which so that the common path is the simpler one. And then when you get to the other VM, you do the opposite. You reconstitute the Lambda from the recipe using whatever translation strategy that VM is using, and instantiate the Lambda object from its recipe. Okay, so we wrap up here. One of the big lessons of this effort was, the path to evolving a language is full of ideas that are obvious and wrong. And you have to be willing to look past your first idea and your second idea and your third idea till you find the actually good idea. In that case, in this particular case, the actually good idea was using Invoke Dynamic to embed a declarative recipe for how to make a Lambda at the, in the bytecode without embedding the details for how to do that. And this gives us flexibility, and it gives us performance. And like I said, even using the stupid strategy, we are as good as or better than interclasses going out of the gate, and there's room to improve in the future. Okay, so a couple places to go for more information. There's lots of documents about Project Lambda at the OpenJDK Project Lambda webpage. There's sort of a detailed overview of the new language features. You can get binary builds. You can go get the public review from the JCP website. And with that, we have a few minutes left. I'm happy to take questions. I see people are leaving. That's fine. Just make sure you do it quietly so the people asking questions can ask their questions. Do we have any questions here? I can't see anything, so. No questions. Oh, there's a man waving his arms wildly. Okay, talk very loudly, sir. So the question is, in the benchmark, the performance for the capturing case, I think what you're seeing is these numbers are throughput. Okay, these are operations per second. Okay, so the non-capturing Lambda gave you more operations per second than the capturing case. The one before that, this is time in milliseconds. Okay, so the non-capturing case was fewer milliseconds than the corresponding capturing case. Okay, do we have more questions? If not, thank you very much.